Let's look at finding the basis of the row space of a matrix. Now, there are a couple of things up here that tell us how to do it, and this theorem is important. But before we look at those, I want to look at two simple examples that we can do by just kind of looking at them and thinking about them. Suppose we had this matrix, 1, 1, 2, 2, 4, 4. We wanted to find a basis of its row space. Well, if you look at these three vectors, 1, 1 looks like that, 2, 2 points in the same direction, and 4, 4 also points in the same direction. So if we wanted to get everything that's in the span of those three vectors, it's just the stuff that's on this line here. So a basis of this row space would just be the set containing 1, 1. And truthfully, we could use any of those vectors. We could use 2, 2 if we wanted as well. But notice 1, 1 is what we get if we were to row reduce this thing. We get 1, 1 there, and the other two vectors, the other two rows get zeroed out. And it's because they're linear combinations of 1, 1 and 2, 2. Or, I'm sorry, they're just multiples of 1, 1. Let's do another example. Suppose we had this matrix, and we wanted its row, a basis of its row space. Suppose we had 2, 0, 3, 1, and 0, 7. Now if you look at those, 2, 0 is going to be something sticking over here. 3, 1 is going to be up there. And 0, 7 is not quite to scale, but it's going to be pointing straight up. So if you look at that, you can get anything in the plane by taking linear combinations of those guys. So if we wanted to, we could take any pair of them and have a basis. But also, another way we could find a basis is just say that's everything in the plane. So the standard basis would work. So a basis of this, basis of the row space, is going to be 0, 1, and 1, 0. And if you were to take this and row reduce it, that's what you'd get, 1, 0, 0, 1, and then 0, 0. So doing these two examples here sort of leads us into this method up here. To find the basis of the row space of a matrix A, you just find the reduced row echelon form of A, and the non-zero rows of that form a basis of the row space. And that's all there is to it. The theorem up here says that if you have two matrices that are row equivalent to each other, then they have the same row spaces. All right, so let's do this example. Let me erase all of this stuff. Let's do this example. Find a basis of the row space of this thing. Well, first up, I'm going to row reduce it. And we're going to do that with octave because that's a big matrix. Already typed it in. So we've got this matrix. And if I take the reduced row echelon form, I get this. So that top row is 1, 0, 1/3, 2/3, 1. Next row is 0, 1, 1/9, 2/9, and -1/3. Then we've got a bunch of zeros below it. So a basis of this would be just those top two rows. So the basis of the row space, I'm going to enlarge this a bit, would be 1, 0, 1/3, 2/3, 1, then 0, 1, 1/9, 2/9, -1/3. All right. So what this is, it's a two-dimensional It's a two-dimensional subspace of R5, I believe. 1, 2, 3, 4, 5, yeah. So that's the basis of the row space. Now, this isn't the only answer we could give for this. And I don't particularly like this answer because it's got all those fractions in it. So here's a nice fact. I probably should have put this on. Probably should have put this on here, but fact: in a basis, you can scale the vectors by non-zero constants. Why is that? Well, if you've got a vector space that's spanned by this vector and this vector, it's perfectly fine to replace this vector with one that's longer, and this one with one that's longer, or shorter, it doesn't matter, as long as it's a multiple of it. So what I can do is come back up here, and if I want to write this with no fractions, I could also say that a basis of this row space is, I'm going to take this top guy and multiply it by 3, and I'll get 3, 0, 1, 2, 3. And the one below, I'm going to scale it by 9 to get rid of the fractions. So it's going to be 0, 9, 1, 2, negative 3. So both of these things, both this and this over here, both of those are correct answers to this. Both of these things are bases of the row space of this matrix.